Welcome to this tutorial on recursion, specifically in Java. What is recursion? So recursion, by definition, is the repeated application of a recursive procedure or definition. Not very helpful, is it? Since it has the word recursive in its definition. In other words, it's kind of defining itself. But this is the idea of recursion. So let's think of it in another way. The idea of recursion is to take a problem and break it down into smaller groups of the exact same problem. In other words, it's to apply the same solution, but on a smaller set over and over again until we reach a point where our solution no longer is correct or works. So here, let's let this rectangle represent our problem. So what I'm going to do is, instead of trying to solve it all at once, I'm going to divide it in two. Now, I still have the same problem, but it's in two smaller sections. I'm going to take that same problem and I'm going to divide it in half again. And 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 again. Until we reach a point where we can't anymore. We have reached our smallest point of dividing in this case, and this is where we are going to stop. And this is what we call in recursion our base case. This is the point at which we stop our recursive calls, and instead we're going to return in order to complete our recursive function. In other words, as we are coming back, we are going to create our solution that will give us our answer to our problem when we get all the way back to the beginning. What is important to understand about the base case is that it is usually the point at which our recursive call, our ability to go in and divide the problem in half or into thirds, whatever it is we are doing, is no longer possible. So let's take a look at our problem, more specifically the idea of factorials. So what is a factorial? A factorial is a multiplication of all the numbers from 1 to the number that we are given next to our factorial. For example, 5 factorial is equal to 1 times 2 times 3 times 4 times 5. 4 factorial is equal to 1 times 2 times 3 times 4. Now, this is where we can have an example of recursion. 4 factorial exists inside of 5 factorial. And so we can actually replace 1 times 2 times 3 times 4 with 4 factorial, meaning that 5 factorial is equal to 4 factorial times 5. 3 factorial is equal to 1 times 2 times 3, which is included inside of 4 factorial. So that means that 4 factorial is equal to 3 factorial times 4. If we continue this pattern, this means that 3 factorial is equal to 2 factorial times 3. 2 factorial is equal to 1 factorial times 2. 1 factorial is equal to 0 factorial times 1. And since 0 factorial times 1 is equal to 1 factorial, and we know that 1 factorial is equal to 1, this means that 0 factorial has to be equal to 1. If we try to continue our pattern, however, we will get 0 factorial is equal to negative 1 factorial times 0. And we know this can't be true, since multiplying by 0 would give us 0, and 0 factorial is supposed to be equal to 1. So, we have reached our base case. We cannot apply our recursive formula anymore, and instead we will stop if we get to 0 factorial. Since we know 0 factorial is equal to 1, we can solve for 1 factorial. Since we'll know what 1 factorial is, we can solve for 2 factorial, which can solve for 3 factorial, which can solve for 4 factorial, which can solve for 5 factorial. This means also that we've created a recursive formula, more notably n factorial is equal to n minus 1 factorial times n. Keep in mind though, this is only true, however, if n is greater than 0. This also means that it is recursive since it uses factorial in its definition to define a factorial. Let's look at another problem, a very famous one known as the Fibonacci sequence. The Fibonacci sequence states that any number in the sequence is the sum of the preceding two numbers, where the first two numbers of the Fibonacci sequence are 0 and 1. So, just based off this definition, we can say that all of this is true. We know that our first number, in other words, the 0th term of the Fibonacci sequence, is 0. We know that the second number, or the term number 1 of the Fibonacci sequence, is equal to 1. And we know that the Fibonacci sequence formula is that for any Fibonacci number, it is equal to the Fibonacci number minus 1 plus the Fibonacci number minus 2, more notably the number before it and the number before that. Keep in mind, this is only true when n is greater than 1. In other words, our n value is at least 2, or we are at least on the third number in the sequence. For example, if we look at the first two numbers and add them together, we should get the third number. Since our first two numbers are 0 and 1, this means that our third number is also 1. If we want to solve for the fourth number, we will add the second and third number in the sequence, which are 1 and 1, and we will get 2. Now let's go take a look at these in code. Okay, let's look at implementing Fibonacci and factorial into code. So we are going to start with factorial by creating a method that returns an integer and requires one integer for factorial. And the way this is going to work is we're going to start first by thinking about what our base case is. As we stated before, our base case is going to be when our number is equal to 0, and we are going to then return 1 since factorial 0 is equal to 1. Outside of our base case, we are going to do a return statement which contains our recursive call. As I mentioned before, our recursive call is the factorial of the number minus 1 times our number. This is all I need to write in order to create a factorial recursive call. I have a return statement at the end which has my recursive call in it, where it will call itself factorial. So you might notice I'm calling my own method inside of me, and it will continue to do this call over and over again until my base case is true. Once my base case is true, it will return, and all of these numbers will solve themselves going all the way back, giving us the result for our factorial. Next, let's look at Fibonacci. I've created Fibonacci, which will take a single number in. This number will be what term in the sequence of the Fibonacci sequence we are at. This means that our base case is if our number is equal to 0 or if our number is equal to 1. This means we are on the first two numbers in the Fibonacci sequence. Both of these first two numbers are equal to 1, so then the method will return 1. Next, we're going to do the same thing we did above and create a recursive call. The recursive call for Fibonacci was calling Fibonacci sequence on a number 1 less and 2 less than it and adding them together, then returning this number. This will also work since what will happen is if we give a number such as 4 will go in here, our base case will not be true, and we will call in Fibonacci on 3 and 2. Those will continue in, both of those will solve, they will go to numbers such as 1 and 0, which will then solve each other, come back, add together, and everything will come back up and add together as our Fibonacci sequence answer. Please keep in mind that when we are doing recursion, we are trying to reach our base case, which will then return and do something to the value we have now been given, resulting in what we need to get as our answer. If we call factorial 4, and for instance, Fibonacci 25, we will get our answers of factorial 4 is equal to 24. In other words, 1 times 2 times 3 times 4. And term 25 of the Fibonacci sequence is 121,393. If you want to check some lower numbers to see if this works properly, now we will try term number 3. Since term 0 is 1 and term 1 is 1, term 2 would be 2, and term 3 would be 1 plus 2, which would be 3. If I use 4, this should be 2 plus 3, which would give me 5. And so that's the basics of recursion. Please keep in mind that the idea of recursion is to eventually reach your base case while returning your recursive formula back once you've returned that to get your answer.